Here's a look at table 7-1, and we'll look at daylight hours. That during an equinox, it's pretty safe to say that we know that the Earth is receiving, all points are receiving 12 hours of daylight and 12 hours of darkness. But what happens when we are in a solstice? Well, it's not the case. So let's look locally. Locally, we will have, in our summer solstice, we will have about 15 hours of daylight, and therefore we'll have about 9 hours of darkness. And therefore, during our winter solstice, we'll have about 9 hours of daylight, and we'll have about 15 hours of darkness. So we can kind of further compare how the axial tilt is acting on our number of daylight hours, and we can look at this graph to help make sense, or this table, sorry, 7.1. That in June, the North Pole is going to receive more solar radiation, about 1,050 Langleys per day, than Chicago and the equator. Chicago gets a value of 950 Langleys per day, and the equator gets about 780 Langleys per day. So the North Pole is experiencing 24 hours of sunlight, and the radiation does not cease. And we can see that here. We can see the Arctic Circle here is completely exposed to sunlight, and it's getting sun full all 24 hours. And that's the importance of these lower values right here, 70, 80, 90. These guys are getting full-time daylight hours for different amounts of time, a couple months, 4 months, 6 months. While the North Pole is experiencing a large amount of solar radiation for 24 hours of daylight, the South Pole is receiving no insolation, 0 Langleys per day, due to being completely dark. And I look at the opposite pole, it's completely dark. So now let's look at these together. So daylight hours and Langleys. So if I look at my daylight hours here, I need to make sure I understand what's going on here with this value of a Langley. Insolation at the outer edge of the atmosphere, measured in Langleys per day, at various latitudes during certain months. So if I look at this picture here, once again, let's talk summer solstice for the northern hemisphere. That during the summer solstice at 90 degrees north, it's actually receiving more insolation, right, measured in Langleys per day, than our local area at 40 degrees north, and greater than that of the equator. And this might surprise you, but it shouldn't once we make sense of, well, it's getting 24 hours of bombardment of solar radiation, whereas the equator's having nighttime for an extended period of time. And we are experiencing, what about 9 hours of darkness, 15 hours of daylight, what about 9 hours of darkness? So here's our value then for the equator would be about 12 hours daylight, 12 hours of darkness. So what we have going on here is we're trying to make sense of daylight hours and Langleys, that the amount of insolation at the outer edge of the atmosphere, we would say that if it's completely being bombarded with sunlight, it's going to have a much larger Langley value, or Langleys per day. So insolation at the outer edge of the Earth's atmosphere at various latitudes. For example, in the Chicago area, the average amount of insolation that the Earth's surface receives in June is 950 Langleys per day. But you'll see that this changes as we move away from June and we move to the fall equinox. So it's going to be decreasing, and eventually it's going to be at its lowest or its minimum in December, and then it's going to begin increasing again until it reaches its maximum. So it's just kind of this ebb and flow of the amount of insolation that's reaching the outer edge of the atmosphere. And we can actually follow these pictures here and see that very thing, the very phenomena taking place here. When it's tilted towards it, we're getting more direct sunlight, greater heat density, we're getting a greater value of insolation located at the outer edge of our atmosphere. And so here's a graphic. Here's a graph that can make sense of that even further. So this is on June 21st. That you'll see that the southern hemisphere, or excuse me, the South Pole, is receiving 0 Langleys per day. And that's really just the understanding. It's fully dark. It's in complete darkness. Remember, June 21st, the northern hemisphere's solstice, summer solstice. That the North Pole is getting 1,050 Langleys per day. And that should surprise you, but it shouldn't after you realize that we're really talking about its full-time sunlight. That a Langley is a unit of energy distribution over an area, and thus is often referred to as heat density. And when I compare the North Pole to having the greatest amount, and it's in this graph as well, Chicago at 40 degrees north, where are we at here? Here we go. We're getting about 950 Langleys per day. So 40 here, about 950. Should be right around here. And the equator's getting about 780 Langleys per day on average, kind of roughly right in here. I don't know, ish, somewhere in here. So when we quantify what a Langley is per day, we can measure it in watts per meter squared. And here's the math that we can. This is actually often quantified as Langleys per hour. It's 24 hours in a day. We get this watt per meter squared. In this case here, we can quantify this in a day period. So we get a Langley day. That's what our value here. We're quantifying this from hours into the day. And we can find that we get this value. This is a constant that we can get, that we can calculate, that's measured in watts per meter squared. So what we have going on here, we're looking at how the daylight hours are going to be influencing the amount of insolation interacting with the outer edge of the Earth's atmosphere at different latitudes at different times of the year. I hope that helps make sense.